Hello friends, in this video I'd like to solve the following problem from the Chinese International Mathematical Olympiad Team Selection Test, 1990, problem number 6. We wish to find all functions f, g, and h from the set of real numbers into itself, satisfying f of x minus g of y equals x minus y times h of x plus y for all real numbers x and y. So here are my hints for this problem. First, set x to be y to express function g in terms of function f. Then, set y to be 0 to express f in terms of h. By this point, you should have a functional equation with only one unknown function, namely h. And now, crucial step, to introduce new function. Let k of x be equal h of x minus h of 0. Express our equation in terms of this new function k. Then show that k is odd, and then change y to minus y to demonstrate that x minus y times k of x plus y equals x plus y times k of x minus y. And finally, set y to be x minus 1, and do verification in the end. So give this problem a try, and I will see you in just a minute. Sorry. Alright, so let's call our equation asterisk. And now let's let's set x to be equal y in asterisk. Well, what then? Then we have the following equation: f of x minus g of x equals, well, on the right hand side we have just 0, which means that for every real number x, f of x equals g of x. Which means that we have already eliminated one function. Right. Now let's set something else. Now let's set, for example, let's set y to be 0, again in our equation asterisk. Then we have the following: f of x minus g of 0 equals x h of x. All right, but remember that f of g of 0 is the same as f of 0, which means that for every real number x, well, f of x is x h of x plus f of 0. Let's also remember that. All right. So using this fact, we can rewrite our equation asterisk. Equation asterisk now becomes the following. Well, instead of f of x, I will put this. And now I am subtracting g of y, but g of y is f of y, but f of y is again something of this form. And that equals x minus y, h of x plus y. Again, f of 0 simplifies, and we have the following equation. All right. You know what? Let's call it, I don't know, double asterisk. Let's call it double asterisk. All right. What now? Now I wish to do the following. I wish to make a substitution. It's a very important step. So now let k of x be equal h of x minus h of 0. All right. Notice that then, first of all, k of 0 is what? It's h of 0 minus h of 0 is 0. And our equation double asterisk can be rewritten in this way. Instead of h of x, I can put k of x plus h of 0. Instead of h of y, I can put k of y plus h of 0. And on the right hand side, we have x minus y. And here we have k of x plus y plus h of 0. And now let's simplify it. X k of x plus x h of 0 minus y k of y minus y h of 0 equals x minus y k of x plus y plus x h of 0 minus y h of 0. Notice that we have some cancellations. X h of 0, x h of 0, minus y h of 0, minus y h of 0. So it all simplifies and it all boils down to the following equation. X k of x minus y k of y equals x minus y k of x plus y. And let's call this equation, I don't know, maybe triple asterisk. It's exactly the same equation as equation double asterisk, but we have k instead of h. Now, let's set something. First, we will set, what we will set? Let's set y to be minus x in our condition triple asterisk. What then? Well, then we have the following. K x k of x plus x k of minus x equals x minus minus x. So it's 2x k of 0. But remember that we have established that k of 0 is 0. So it's 0. Which means that in particular, for every real number x, k of x plus k of minus x equals 0. Again, why is that? Well, I'm just dividing by x. If I divide by x, I have this equation. But you may ask, what happens at 0? If x equals 0, then we cannot divide by 0. But if x equals 0, then we have k of 0 plus k of 0. K of 0 is 0, so this equation still is true. All right. In other words, i.e. k is odd. Our function k is odd. All right, so now I will do the following. I will now change, I will take equation triple asterisk, and I will, for example, change y to minus y. Let's do it. Let's change y to minus y in equation triple asterisk. What then? Then we have the following equation. Well, we have k x k of x minus y, but it's plus y k of minus y equals x plus y k of x minus y. But now let's take a look. We have established that our function is odd. So k of minus y, it can be written, we can put minus in front of our function. Yes, I have used the fact that my function is odd. Because k is odd. All right, but now look closely. This expression, which stands on the left-hand side, is what exactly? X k of x minus y k of y is exactly the same as x minus y k of x plus y. It's exactly the same. Yes? Just look at the equation triple asterisk. All right, now we have something. So this equals that for all real numbers x and y. In particular, I will set y to be equal x minus 1. Then we can derive the following fact. X minus y is 2x minus 1. 2x minus 1. Or you know what? No. Maybe I will do something else. All right, let's do it. Okay, 2x minus y, 2x minus 1, k of 1 equals 1 times k of 2x minus 1. No, it's all well and good. It's all well and good. Everything right? Yes, it is. All right, and now that means x is arbitrary. Our function is linear. So for after changing arguments, for every real number x, k of x equals k of 1 times x, i.e. k is linear. So now we can write the following. Since our function is linear, we can write that k of x equals ax for some real number x. And now let's go back to h. Maybe I will write it in. Right. K of x equals a times x. But what is h of x? Remember that h of x can be expressed as k of x plus h of 0. But again, h of 0 is some constant. Let's call it b. So h of x equals ax plus b. All right. And what about f? What is f of x? Well, f of x, let's go back. F of x. Remember that f of x is x times h of x plus some constant, another constant. So it can be written as ax squared plus bx plus c. And what about g? Well, remember we have demonstrated that f equals g. So we have ax squared plus bx plus c. So it looks like that our solutions should be the following triples of functions. F of x equals g of x equals ax squared plus bx plus c, and h of x equals ax plus b, where a, b, and c are real constants. All right, but now, very important, verification. Let's verify. Verification. So let's compare the left-hand side with the right-hand side. On the left-hand side of our equation, very first functional equation asterisk, we have f of x minus g of y. Well, f of x minus g of y is ax squared plus bx plus c minus ay squared minus by minus c. And this is ax squared plus bx minus ay squared minus by. I can write it in the following way. I can factor out x here. So we have ax plus b minus, and here I can factor out y. All right, but remember what is ax plus b? Well, it's just h of x. H of x. Or you know what? No, maybe it goes south. So maybe let's just write the right-hand side. X minus y, h of x plus y. So it's x minus y a x plus y plus b, which is what exactly? Let's see. So it's x minus y, ax plus ay plus b. So it's ax squared plus axy plus bx minus axy minus ay squared minus by. And this is, after some cancellations, it's exactly the same. Ax squared plus bx minus ay squared minus by. Exactly the same. So for any real parameters a, b, and c, any triple of solutions defined right here is really a solution. So we have, in fact, infinitely many solutions. And that closes our problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.